Hey everyone, ready to get a little nuclear today?
Sounds dangerous.
Don't worry, it's all good. We're talking fusion energy.
Oh, okay. So more like the future of clean energy then.
Exactly. We're diving deep into how researchers are using AI to speed up the race to make fusion power a reality.
It's a wild combination, that's for sure. Cutting-edge physics meets serious machine learning.
And it could have massive consequences for the future of clean energy, right?
Huge. But before we get ahead of ourselves.
Good point. Always good to start at the beginning. For those of us who may not have a PhD in physics, what exactly is fusion energy? Why all the hype?
In the simplest terms, it's like trying to bottle the sun. Fusion involves forcing atomic nuclei to merge, to fuse together, and when that happens, boom. Huge release of energy.
Way more than regular nuclear power, the fission kind.
Way more. Orders of magnitude greater.
Okay, so that's the energy part. But everyone calls fusion the holy grail of energy. What makes it so special?
Well, unlike fossil fuels, it doesn't release greenhouse gases. And compared to fission, there's very little radioactive waste. Plus, the fuel source, practically limitless.
Oh, clean, powerful, and abundant. It really does sound too good to be true.
And that's the catch.
Ah, there it is. There's always a catch. What's standing in our way?
Replicating the conditions inside the sun here on Earth is anything but simple.
I imagine it gets a little toasty.
A little. One of the biggest hurdles is finding materials that can withstand the insane temperatures and intense radiation bombardment inside a fusion reactor.
So we basically need to build a container that can hold a star. No pressure.
Pretty much. And that's where this research paper we're looking at comes in. It focuses on a massive international project called the IFMIF-DONES project.
IFMIF-DONES.
Catchy.
Right. It stands for International Fusion Materials Irradiation Facility Demo-Oriented Neutron Source.
I'll take your word for it. So this facility, it's purpose-built to test materials for future fusion reactors. Precisely. Now, before they build anything, they need to simulate how materials will hold up when blasted with neutrons, right? And that's where things get really interesting and where the AI comes in.
I was wondering when we'd get to the AI part. So instead of building a zillion tiny test chambers, they're simulating this neutron bombardment on computers.
Exactly. Think sophisticated computer simulations. The paper specifically focuses on something called Monte Carlo simulations.
Monte Carlo, like the casino. Are we rolling the dice with fusion research now?
Haha, not quite.
Yeah.
But there is a connection. See, these simulations involve modeling the behavior of billions, even trillions of particles. Kind of like predicting every possible outcome of countless dice rolls.
That sounds incredibly complex.
It is complex, yeah. These simulations are the gold standard, the most accurate way we have to predict how materials will behave inside a fusion reactor. But there's a but.
Uh-oh. I don't like the sound of that but.
They're incredibly computationally expensive. We're talking simulations that can take days, even weeks to run, even on the world's most powerful supercomputers.
So we have this incredible tool, but it takes forever to get results. I bet you're about to tell me AI can speed things up.
You know me too well. That's the million-dollar question this research tackles. How can we use AI to create shortcuts?
Okay, I'm all ears. Tell me more about these AI shortcuts.
We're talking about something called deep learning surrogate models, DLSMs for short.
Catchy?
Right. And here's the magic. They learn from the data produced by those super slow, super complex simulations, feed that data into a sophisticated AI system, and it starts to see the patterns, the relationships.
So it's like the AI is learning to mimic the results of these complex simulations without having to actually run through the whole time-consuming process.
Exactly.
So instead of waiting weeks for an answer, the AI can, just sort of spitball a prediction based on what it's learned.
You got it. And the paper explores two different ways to build these DLSMs, these AI shortcuts.
Okay, heavy.
The first one they looked at is called a multi-layer perceptron, MLP for short.
MLP sounds almost friendly.
Deceptively simple name, really. It's a classic type of artificial neural network. The kind of AI that's been used for everything from, image recognition
Right, yeah.
to natural language processing.
So the MLP, it's like the old reliable in the AI world.
You could say that, but even the most reliable tools have their limits.
What's the limitation here?
Well, in the case of these fusion simulations, the biggest challenge is that MLPs usually need a ton of data to be trained effectively.
Ah, I see where you're going with this. Remember those limited flashcards we talked about?
Exactly. Not ideal when each flashcard, each simulation, takes days, maybe even weeks to generate.
So not exactly a quick study, this MLP. What's the alternative?
That's where the deep operator network struts in. DeepONet for short. This one's a bit more specialized. It's really good at learning from limited data, which is perfect for our situation here.
Okay, so we've got our MLP, the seasoned veteran, but a bit slow,
Right.
and our DeepONet, the quick learner. They both walk into a fusion reactor. What happens next?
Well, the researchers put them both to the test, and they actually included some visuals in the paper to show us how it all went down.
Love a good visual. What they show.
There's a graph, figure 2 in the paper, that I think illustrates this really well. It basically shows how well each model could predict certain material properties.
Okay, like what? Give me an example.
Things like how much heat the material could handle before it starts to,
Melt.
exactly, or how resistant it would be to damage from all those neutrons. And they looked at how the accuracy of these predictions changed based on how much data each model was trained on.
Okay, so, pop quiz time. How'd our contestants do?
With limited training data, the MLP, well, it struggled, kind of like trying to predict the weather with only a couple data points.
Not very reliable.
Not at all. The DeepONet, on the other hand, it aced the test. Even with fewer simulations to learn from, it could still make surprisingly accurate predictions about how the materials would hold up.
Wow, so it's like the DeepONet was able to figure out the underlying physics, even with less information.
Exactly. It was able to generalize from the limited data much better than the MLP.
Impressive. But we're talking about speed here, right? How much faster are we talking?
Buckle up. The DeepONet achieved a speed-up factor of over 9 million.
Hold on. 9 million.
You heard that right. What used to take weeks of number crunching on a supercomputer could potentially be done in seconds with the DeepONet.
Okay, now that is a shortcut. I'm starting to think this DeepONet is the real deal. But every AI has its quirks, right? What are the caveats here?
Well, in the interest of full transparency, the researchers were very upfront about the limitations of their work.
Always appreciate that.
For one, their simulations were mainly in 2D, meaning they were simulating a flat slice of a reactor, not the whole 3D structure.
Makes sense. A real-world fusion reactor is a bit more complex than a flat slice.
Right. They also focused on one specific type of fusion facility.
So no guarantees the same results would translate to other reactor designs.
Exactly. And to be clear, they don't see these AI models as a complete replacement for full-scale simulations. At least not yet.
So there's still a need for those good old-fashioned supercomputer simulations. For now, at least. But still, the potential here is undeniable. Where do the researchers see this going in the future?
That's what I find so exciting. Even with the limitations, they're incredibly optimistic about what AI can bring to the table when it comes to fusion research.
Like what? Give me the dream scenario.
Well, for one, they believe these models could eventually handle those complex 3D simulations.
Even more accurate predictions.
Precisely. And they even talk about using something called reinforcement learning. Imagine an AI that can actually learn to optimize the fusion process itself, making adjustments on the fly based on the data.
So the AI becomes like a virtual fusion conductor, fine-tuning the reactor in real time?
You got it.
That's amazing.
And there's one more thing. They also mentioned something called physics-informed neural operators.
Peons. Catchy.
Right. It might sound a bit whimsical.
Just a pad.
But it's a fascinating concept. Basically, pianos are designed to bake the fundamental laws of physics directly into the AI's learning process.
Okay, so instead of just crunching numbers, the AI would have a fundamental grasp of how physics actually works.
Exactly. It's about merging the best of both worlds. The raw computational power of AI combined with centuries of scientific knowledge.
It's pretty mind-blowing when you think about it. Combining the power of AI with, like, the elegance of physics.
Yeah.
But this paper, it focuses on making these simulations faster, right?
Right.
But could this type of AI acceleration be applied to other areas of fusion research too? What are your thoughts?
That's a great question. And it's where this paper gets really thought-provoking, I think. It's not just about making what we already do faster.
It's about opening up entirely new paths of exploration, stuff we haven't even thought of yet.
Exactly. I mean, this paper looks at material testing, right?
Right.
But imagine using AI like this for other parts of fusion research, like plasma confinement.
Which,
how you contain the superheated gas where fusion actually happens.
Oh, right.
Or even designing entirely new types of fusion reactors, things we can't even picture yet.
It's pretty wild to think that we could be on the verge of a fusion revolution.
It's possible.
And AI might be that final push that makes it a reality.
It really could be. It's a future full of potential, that's for sure.
Well, I'm excited to see where it all goes.
Yeah.
This has been an incredible look at how AI is shaping the future of fusion energy.
Absolutely.
If you want to learn more about this groundbreaking research, you can find the full paper linked in our show notes.
Definitely worth a read.
And as always, keep those brains buzzing and never stop exploring. Thanks for joining us.